Even for a person with a big heart, the heart is actually still very, very small. Yet it's so powerful, full of natural technology, it is really impressive. Wouldn't it be amazing if we could just look inside my chest to have a better look at the heart? Whoa! Now we can. Thanks to these amazing 3D platforms like Visible Body, you can just look inside the heart, rotate it, zoom in, zoom out. Absolutely amazing. Welcome to Friday Physiology. The heart is literally the motor of the cardiovascular system. It's positioned in the middle and sends blood into the arteries, into the pulmonary circulation and back to the heart. And then through the arteries and arterioles to the systemic circulation and finally to the capillaries where the actual exchange occurs. The veins will take the blood back to the heart, and that's where the whole cycle starts again. More than 50% of the blood volume is just water, mixed up with some minerals. The hematocrit value is the percentage of total red blood cell volume in relation to total blood volume. The heart is a discontinuous pump and is basically one big muscle that will contract systole and relax diastole with a frequency of approximately 1 beat per second at rest. From the outside, you can distinguish different layers, but clearly the myocardium is the layer that generates all the power. For the basic anatomy of the heart, I can strongly recommend using the Visible Body or any other 3D platform so you can really explore every aspect and you can develop a clear 3D image of the heart. In this video, we will focus on the functional anatomy as we will name the functions of the major components step by step. The heart has 4 different compartments, 2 atria and 2 ventricles. And each of these compartments are separated either by walls or by one-way valves. During the diastole, the blood will flow from the atria into the ventricles as the AV valves are open. As soon as the systolic phase has created enough pressure to push the blood back up, the AV valves will automatically be pushed to close and the semilunar valves open shortly after to allow the blood flow out of the heart into the pulmonary artery into the aorta. The normal order of blood flow is blood enters in the right atrium, it will flow into the right ventricle, it is then pushed into the pulmonary artery through one of the semilunar valves. The blood passes through the extensive network of capillaries to get rid of CO2 and to allow O2 to diffuse into the blood. The blood returns back to the heart into the left atrium. The left AV valve is open to allow blood flow into the left ventricle, and during the next contraction, blood is pushed out into the aorta to serve the entire body with oxygen-rich blood. And the whole cycle starts again. If you would take the heart out of the body and just supply it with some ATP, it would beat at a frequency of 100 beats per minute, thanks to some ion leakage inside the SA node. My heart rate is around 80 beats per minute at this moment and is influenced by physiological, psychological, and autonomic factors. In a healthy situation, the SA node is always the start of the electrical pathway. From there, the electrical signal will spread across both atria to allow the atria to contract together, pushing this last extra bit of blood into the ventricles. As soon as the electrical signal will reach the relay station between the atria and the ventricles, the AV node, the signal will go straight towards the apex of the heart and from there will move upwards from cell to cell. It is essential that the contraction always starts at the bottom and the cells depolarize in that same order, from bottom to top, to literally squeeze the blood into the right direction, that is out of the semilunar valves. Fibrillation is an example of inconsistent depolarization of the cardiac cells, resulting in chaos, complete loss of stroke volume with potentially even fatal consequences. In a normal situation, depolarization is spread from cell to cell via gap junctions, and the signal moves only in this correct upwards direction. To up and down regulate the heart rate, your body uses the sympathetic and parasympathetic input in a similar way as you would use your gas and brake while driving a car. To slow down, you could either release the gas or hit the brake. To lower the heart rate, you can do the same. Either lower the sympathetic input or increase the parasympathetic input. During exercise, the opposite will happen. Parasympathetic input will decrease while sympathetic input will increase. Not only will that affect the heart rate, but it will also increase the contractility of the heart. Cardiac output is increased by an increase in the two underlying components, heart rate and stroke volume. With an ECG, you can measure the underlying electrical flow through the heart in 3 dimensions. For a young physio, this might look very overwhelming, but if you can memorize the alphabet and the order of blood flow through the heart, you can also understand all these components of this ECG. Do you remember these safety instructions in an airplane? Please put on your own oxygen mask first before helping others. That is great advice, and the same applies to the heart. Before it can serve the rest of the body, it first needs to put on its own oxygen mask. And even though the heart is constantly filled with fresh blood, it cannot extract oxygen from the inside. It needs to get blood through the outside, through the coronary arteries. And although the heart's anatomy and physiology is almost perfect, you could see this, its own blood supply, as one of the weak points in the design. At rest, the heart already extracts 70 to 80% of all the O2 available. During exercise, therefore, blood flow to the heart should go up in the same way as the overall energy consumption goes up. If the whole body needs more O2, the heart needs to pump harder and therefore also needs more O2 itself. If the oxygen supply to the heart cannot keep up with the demand, for example because of a narrow coronary artery, you can develop signs of angina. Or worse, if the oxygen supply is completely blocked to some areas of the heart, you can develop myocardial infarction, a heart attack. And some of the cardiac cells will die, and depending on the size of the damage, stroke volume will be affected. For any young physio, it's crucial to understand the different types and levels of cardiac patients, and to see how stroke volume and cardiac output are affected by the pathology. In some cases, surgery might give the patient some relief, for example via an extra bypass or a new valve. But at the end of the day, it's all about exercise and training, and that's where you come in. As a physio, you need to understand which physiological variables are permanently affected by the pathology, maybe to work around it, and which variables you can still target in your exercise program. I hope you will take my advice to heart. See you in the next video.